conceptually, when we think about our area between of a region between two curves, we can really think of this as an accumulation process. This is something we stated in the very first video in this series. Formally, we take that area to be accumulation of some representative element under the curve to obtain a new integration formula. And to visualize that situation, let me give you sort of the rundown as we're looking at this graph right here and what that might mean. So, if we consider this curve y equals f of x, that is our known pre-calculus formula. As a matter of fact, we could set it up between any two curves. We're going to take our second curve to be y equals 0 right here, and we're going to have y equals f of x to be this upper curve, whatever it is on this curve. So this is our known pre-calculus formula. Now, what we're going to do is that when we said this was a limit as as n goes to infinity of these number of rectangles that we were building under the curve using the Riemann sum, each with a width of dx. So dx right here is our width of our representative element. Then each of these representative elements, as we go from left to right, accumulate in area. Perhaps by small widths of dx, but if we have an infinite number of those dx widths, we can build them up to get the total area from A to B. Well, let's limit ourselves to just looking on a small little element right here from -2. Let's say we're starting over here at this point A. So we're going to start over here at A, and we're going to go to some value, and we'll call it x sub 2. What could we say? Well, we could say that the area that has accumulated between A and this function x of 2 is going to be a new integration formula. That is, we're going to go from A to this point x sub 2 of our function f of x minus 0 dx right here in this particular process. And this is going to give us, in fact, a new function. And we're going to consider that function to be f of x sub 2 minus f of x of a. And if we evaluate this new integration formula, what we're going to get is a new function. This is our new integration formula. Now, in most cases, we're going to go from A to some fixed point x of 2, like we might go all the way from A to B and find the total area under this curve. But if we imagine this is an accumulation process, as dx is moved from left to right, as our representative element moves from A to B, the area that accumulates behind that curve is our function. And so what we're going to do, we can almost associate this with our function. At A would be 0, right? But if we were to go through, at least in this particular curve, over x, we can almost associate this with our second fundamental theorem of calculus, right? You recall that if we took a derivative of this particular function at any point, well, we would certainly get f of x, the derivative of our original function, right? If we had this function at some unfixed value x right here, right? You can see there's sort of a connection right there. All right, well, what does all of this mean? Let's consider the area enclosed by the x-axis right here, and the curve f of x equals 4 minus x squared. We would want to find the accumulated areas from f of -1, f of 0, and just show the general formula f of x of 2 right here. Okay, our starting point A has to be -2, right? That's where our curve f of x is equal to 4 minus x squared. And if we were to go all the way to B, that would be at 2 over here. So what we're going to do is we're going to consider our accumulation process, f of x, to be the antiderivative, the derivative our definite integral, starting at negative 2 and going to some point x of the function 4 minus x squared dx. So if we were to build this accumulation process function, this accumulated area is going to be equal to, let's see, 4x minus 1/3 x cubed when we evaluate this from negative 2 to x. Let's see. So, you know what? I'm going to call this x2 because I've already got an x in here. I'll call this x2. So we're going to get 4 times x2 minus 1/3 of x2 cubed minus, let's see what happens right here, 4 times 2 minus 1/3, negative 2, pardon me, of negative 2 to the third. All right. This is going to become 4 times whatever x2 is minus 1/3 of x2 cubed. Let's see, and if we work this one out, minus 16/3. All right, so if we're going to evaluate f of x2, which is the last one, right, this is what our formula would look like. And we can see what this formula is going to look like at different points. For example, it says, well, let's find what happens at f of negative 1, right? That's the accumulated area to the left of negative 1, right? Well, to the left of negative 1, that's going to be the same thing as negative 4 plus 1/3 minus 16/3, which is to say negative 4 plus, let's see, 1/3 and negative 16/3 is negative 15/3. That's negative 5. Does that work for? Minus negative, that should be plus, right? Plus 16/3, my error. So this is going to become plus, in this case, plus 17/3. There we go. And of course, 4 is 12/3, so we take that away. We're going to get 5/3 in this particular case. If we say f of 0, of course, that means we're just going to have 0 minus 0 plus 16/3, so we're going to have 16/3 as our area accumulated to the left of 0. That's thirds. Better not say thirds and 0 at the same time. I'll get myself confused. So this is it. This is the accumulation process that we can think of right here. And this is one of the reasons that we do, when we draw these formulas, get these representative strips to kind of help us visualize that process.